Good evening to all. I am Karthik, Assistant Professor, Mechanical Engineering Department from SNS College of Technology. In this lecture series for this month, we have seen about different heat treatment process and the two most important and crucial diagram which plays a vital role in heat treatment process, which is TTT diagram, time temperature transformation diagram or isothermal diagram. So following that, we are going to see the another important diagram, graphical representation, which is known as continuous cooling transformation, which is CCT diagram, a graphical representation used to understand the transformation of austenite into various microstructures such as pearlite, bainite and martensite in steel during continuous cooling process. So unlike time temperature transformation, that is TTT diagram, which is used in the isothermal condition, the CCT is more practical for real world cooling process, where the temperature continuously decrease rather than holding on to a constant temperature. In CC diagram, in vertical axis is temperature similar to TTT diagram. This typically ranges from above austenite temperature down to room temperature. In horizontal axis, usually a logarithmic scale represents the cooling time. And critical lines and curves, the transformation start and finish curve. These lines indicates the beginning and end of a transformation as the material cools. So the nose in the CCT diagram represents the shortest time where the transformation starts during the continuous cooling, typically in the moderate cooling rate. RS lines indicates the start AR1 and finish AR3 of transformation regions. When takes the phases and microstructure, first one is pearlite phase, forms at high temperature and slow cooling rate. The CCT diagram shows pearlite formation over a range of cooling rate that are slow enough to allow carbon diffusion. The second one is bainite, forms an intermediate cooling rate and temperature where cooling is faster than that required for pearlite but slower than that of martensite. In martensite, forms a rapid cooling rate, typically seen at the far right of the CC diagram, where the cooling curve bypasses the nose and of the pearlite and bainite region, indicates the transformation at low temperature without diffusion. So the main usage of CCT curve is to determine the cooling rate. So the cooling rate followed on the CCT diagram can be used to predict the resulting microstructure. For instance, a slow cooling rate might follow a path through a pearlite region, while a rapid cooling rate could pass pearlite and bainite region, resulting in martensite. In predicting mechanical properties, the final microstructure indicated by the cooling curve on the CC diagram helps in predicting the mechanical properties of the steel, and the different microstructure like a pearlite, bainite and martensite have distinct properties in terms of hardness, strength and toughness. So in cooling path, a very slow cooling, the cooling curve might pass through the pearlite region, resulting in microstructure predominantly composed of pearlite, while provides a good balance of strength and ductility. In cooling curve could pass through the bainite region, leading a bainite structure which offers a combination of high strength and good toughness as a moderate cooling. On rapid cooling, which is quenching, the cooling curve bypasses the pearlite and bainite region, as I said already, resulting in martensite structure, which is very hard and brittle. The structure typically requires tempering to adjust or to alter the property for the practical use. So in practical application, the heat treatment design, CCT diagrams often used to design the heat treatment processed by the selecting appropriate cooling rate to achieve desired microstructure and mechanical properties. Second one is quality control, to ensure the cooling rate during manufacturing conform to desired path on the CC diagram to produce the intended microstructure. In field analysis, investigating failure by comparing actual cooling rate and resulting microstructure against the predicting of CCT diagram. When compared to TTT diagram, CCT diagrams are more applicable for real world scenarios where cooling is continuous, unlike TTT diagram which assumes isothermal conditions. In cooling rate, CC diagram illustrates the effect of different cooling rate on microstructure, where TTT diagram shows the effect of time at constant temperature. In creating TTT diagram, we have some experimental procedures. First one is austenitizing, heating the steel to form a homogeneous austenite. Controlled cooling, cooling samples at various cooling rate and reducing the recording the transformation and start to finish in temperature. The third one is microstructure analysis, analyzing the resulting microstructure using microscopy to determine the phases formed at the different cooling rate.